Good morning, everyone. Welcome. My name is Krzysztof Opasiak. For some non-Polish speakers, Chris is really good enough. Today, I would like to tell you a few words about the USB and its implementation in Linux on both host and the device side. Well, in my personal opinion, USB is the most common external interface in the world. Thousands of people are using it every day, but most of them doesn't even have idea about its design and its consequences. So let's start with some schedule. First of all, I'd like to give a gentle introduction to the USB protocol. Then we will go through one of the most recognizable features, the plug-and-play philosophy. We will see how bad USB attack works, and I will try to show you how you can easily create your own USB device on a Linux board. Okay, what USB is really about? Well, USB is about the same thing as the internet. It's about providing and using a service. Of course, a different type of service, because instead of HTTP, we have the storage, printing, Ethernet, maybe your camera, but it's still a service. The general architecture consists of the USB device and the USB host. USB device is a machine which provides some service, provides some additional functionality to the USB host. Single USB device may provide multiple functionalities. So in one physical device, we may have both camera and pen drive, for example. How we connect our device to the host? We use a cable with 4 wires. 2 of them are used to provide the power, and 2 of them are used for differential transmission to eliminate the symmetric noise. In USB 3.0, we have 2 additional pairs of cable and to increase the speed. We have the wires, we have the host and the device, so now we can connect them. On a physical level, we connect them into 3 topology. We have our host. It has some number of 3 USB ports, so we may connect their normal USB device, or we can connect their a special type of USB devices, which is called the USB hub, which can extend the number of our ports in the host. So we will get a 3 topology like this. But on a logical level, USB is a point-to-point protocol between host and the device. There is no way of communicate between 2 devices. You always communicate between one of the devices and host. So what USB device really is? Well, first of all, it is a piece of hardware which is used to communicate in USB device mode. This is a little bit equivalent of the network card from the internet world. So you need some kind of hardware to communicate on electrical level. When you have this hardware, you may implement the USB protocol using this hardware, so you are able to speak a common language with the host. If we are able to speak, so now let's use our speech to provide something useful. So we need some kind of communication protocol on the top of the USB protocol to provide additional functionality to the host. If you would like to provide something, then we need to have what to provide. So we need our executive element. For example, additional storage, the flash storage in our pen drive, it's a kind of executive element, so we are passing this to the USB host. Endpoints. The communication in USB always happens between the USB host and one of the endpoints of chosen device. Single USB device may have up to 31 endpoints and not less than 1 endpoint, which is called endpoint 0. Each of endpoints has a unique address, so we are able to identify them. Endpoint 0 is the only one which is able to transmit the data in both directions. All other endpoints are unidirectional. And here is a tricky thing. USB is a host-centric protocol, so the direction of the endpoint is always called from host perspective. If we say that endpoint is in, it means that it is able to transmit the data from device to host. If endpoint is out, then it is capable to transmit the data from host to the device. In internet world, we have generally two types of communication. We have the TCP and the UDP. In USB, we have 4 different types of transfers. The first one, the control one, is reserved for endpoint 0. It is used during discovering the device capabilities. This process is called enumeration and can be later used by the application. The next one is the interrupt. It is used when we would like to transfer a small amount of time-sensitive data like our mouse movements or keystrokes, all that kind of stuff. The most common one, bulk, it is used to transfer a large amount of non-time sensitive data. So we have a bunch of data, I would like to just transfer it when the bus is free. ISO is the last type, and it is used to transfer a large amount of time-sensitive data, but without guarantee of delivery. So it's used to transfer the audio or the video streams, as it is better to drop a frame than delay the whole stream and the retransmission. From the logical point of view, a USB device has endpoints, and those endpoints are grouped into interfaces. Interface is a group of endpoints which are required to provide some well-sandboxed functionality. Interfaces are grouped into configurations. Configuration is a group of interfaces which can be used in the same time. Single USB device may have multiple configurations, but only one of them can be active in the same time. USB bus itself on a low level. Well, on a low level, USB is a host-controlled bus. It means that nothing on the bus can happen without host first initiating it. Even if you have transfer from the device to host, this transfer on low-level version of the protocol is initiated by the host. So the host says, now I would like to get some data from you. USB is a pull bus. It means that host constantly pulls each device sending or requesting the data. Plug-and-play philosophy. Generally, this philosophy is about, OK, I have some new device. Now I would like to connect this, and everything should be configured and discovered, loaded, set up, and it should simply work. How it works under the hood. First of all, user has to plug in the device. Most of the wired connection works better when they are really connected. So USB also follows this principle. Then host needs to detect the connection. So we have the connected event. Choose some address, because each USB device on a bus has a unique address which is used to address the communicates to this device. Then host needs to get some information to discover the device capabilities, whether it is the USB web camera or it is the USB pen drive or anything like this. If we know what our device offers, we may choose one of available configurations. Then we need to choose drivers for each interface. Yep. In Linux system, drivers which provide something to user space which makes our device useful are chosen for the interfaces, not for the device as a whole. So each interface may have a different driver. Why it is done in this way? Well, as USB device may be a composed device and offer multiple different functionalities, there is no point in creating a driver for each subset of the functionalities. So we have individual drivers for each functionality. OK, how we get the device information? Well, each entity in the USB world is described with data structure called the descriptor. Each USB descriptor has a common header, so we are able to easily identify it. OK, the most important descriptors. First of all, we have the descriptor for our USB device as a whole. First of the important fields are ID vendor and ID product. The ID vendor is the identification number which is assigned by the USB organization to the manufacturer of this device. ID product is the identification number of the product which is assigned by the manufacturer. Then we have the class information in the device descriptor, and the same class information may be repeated in the interface descriptor, because each interface may belong to different class. What is this class? Well, we have the audio, we have the human interface, and all that stuff. What does it mean that device belongs to some class? Well, it means that it implements some well-defined standardized protocol. So instead of using a vendor-specific driver, we may use a generic one, because all those devices which declare such class should be compatible with the standard. Then in device descriptor, we have also 3 human readable strings, the manufacturer, product, and the serial. To be detailed, those strings are stored in the strings table, not in the descriptor itself, so that's just the index which allows you to get those strings. Of course, there is nothing which enforces that serial has to be unique. So you may buy 10 pen drives from China, and each of them may have the same serial number. Sorry. Each configuration may have a different max power. What does it mean? This field declares how much power the device needs to drain from the host to work in this configuration. We have also the endpoint descriptors, so we have the endpoint address, the attributes, which generally informs us about the type of the endpoint, control, interrupt, ISO, control no, because there is no descriptor for endpoint 0. It is the only endpoint which is not grouped into interfaces. It is always available, and we may always speak with that endpoint. Okay, so short summary. What information are required for us to choose a suitable driver? ID vendor, product, class information, max power, so it is used to choose the configuration, and the interface information about the class. When we discovered what our USB device really offers, we need to choose one of the available configurations. Well, how to do this? First of all, we need to have enough power for this configuration. If we have to ask if it has at least one interface. If the device has only one configuration, there is no problem. We just simply take this one and go. If device has multiple configuration, then our kernel does some heuristic and says, OK, Linux is not the most popular desktop OS yet, so let's choose the configuration in which first interface is not vendor-specific class, as we are more likely to have a driver for a well-standardized protocol than some vendor-specific driver. When we choose a configuration, all interfaces from that configuration becomes available to our USB host. So now we have to choose a driver. What this driver really is. In this presentation, when I refer to the USB driver, I think about the piece of kernel code. We are able to drive the USB device from the user space using libUSB, but now I will focus on the kernel drivers. Such driver usually provides something to user space which makes our USB device usable. So this driver is really only a translation layer between our generic request from the user space, using, for example, block device, network interface, TTI port, and translates those generic Linux commands into commands from the protocol of the device. So when we are sending a network packet, for example, it simply wraps it into protocol which is understandable for the device and sends the packet to the device. How to choose a suitable driver? Each driver which we are focusing on is described using struct USB driver. And when the device needs a special handling, we will choose our driver using the vendor ID and product ID informations. If driver implements some well-standardized protocol, usually we would like to use the class information of the interface. If we are using the class information, no matter what is the vendor ID and product ID. This is why many pen drives from China really works, even if their vendor ID is 123 and the product ID is 345. Because they have correct class information, so all those devices are sharing the same driver in the kernel. It's a USB storage driver, for example. The big picture. We have our USB device, the USB bus, host controller, its driver, our struct USB device, multiple interfaces from current configuration, driver for each interface, and those drivers provide something to the user space, for example, the network interface or input source to our X11 if this is a keyboard or something like this. What next? We have a driver. We have provided something to the user space. So what is happening next depends what we have provided. If we have provided the network interface, probably our network manager will take care of this. If we have provided a block device, because this is a pen drive or something like this, probably our auto-mount service will take care of this. If we have provided the mouse or the keyboard, so the input source, X11 automatically will start using them. And many other things will happen automatically without any user action. And this is the main reason why badUSB attack works so well. So some security summary. There is no user interaction between plugging in the device and moment when the user space starts using it. Everything happens automatically. Drivers are probed automatically. User space starts using new device automatically. And the device may introduce itself as it wants. There is no cryptography, there is no digital signatures or anything what ensures that there is any relation between physical output of the USB device and its logical implementation. So a short demo now. Well, what I have prepared here is a tablet. Do you agree that it looks like a tablet, feels like a tablet, smells like a tablet? So probably it is a tablet. It is even turned off, so we will have to wait a little bit. And what I will do now, I will try to connect this to my computer, and we will see what will happen. Waiting, waiting. Android is booting. Oh my gosh, it's so fast. So, still waiting. Sorry for this. I should have done this before, but I didn't. Oh, my fault. Waiting, waiting, waiting. Is there someone who is developing Android and know why is it booting so slow? Still waiting. OK. So I have some application here, and I have connected a tablet. So probably I would like to take my pictures or maybe play some music or the movie to the tablet. But different things may happen. For example, I have connected the tablet, but it opened the terminal. Whoops. It opened another one. Whoops. It's trying to download something from the net. Whoops. it changed the desktop background. How is this possible? I have just connected a tablet, nothing more. It's not the keyboard, it is not some weird USB device. It's only a tablet. Well, yes, it is possible. Because I have connected a USB device. And hardware inside that device is only used to communicate. Everything what is on the top of the USB protocol is being implemented in the software. So there is no relation, definitely no relation between physical output of the USB device and its implementation of the logical level. So this device looks like a pen drive, but it sends the descriptors taken from my keyboard on my desk in work. It implements the human interface protocol, so it behaves exactly as the keyboard. And what it does, it simply sends the keystrokes, open the terminal, write the command, and do all the stuff. How dangerous it is? Well, what I have done, I have opened the terminal and run some commands. So this attack can be used to execute any arbitrary command which currently logged user can execute. Anything. So, for example, rm-rf home, etc. How we can protect? Well, we may stop using USB. Probably none of you will go this way. We may try to limit the number of input sources to X11, but it's not perfect. It has many problems. So let's use kernel feature, which is called the USB device or USB interface authorization. There are some projects currently developed on the GitHub. For example, the USB guard, it's using this kernel mechanism. It gives us the time to check what we have really connected. So how it works. Each USB device has an authorized attribute in its sysfs directory. Each host-controlled device has the authorized default attribute in sysfs directory. If we set this attribute to some value, each newly connected USB device will get this as a default value for the authorized attribute. If the authorized attribute is set to false, then drivers for the USB interfaces are not being chosen. So it means that this device is unusable. There may be no communication between host and that device in a different way than communication to endpoint 0 to detect the capabilities of the device. What it gives us? Well, it gives us time. And the time is really valuable here because it gives us time to check what we have really connected to our computer. So my tablet, once again. It's not this terminal, this one. So I will do ls-usb. And this device is currently a tablet. It introduced as a Dell computer, so because I have a Dell keyboard, and I took the descriptors from there. So it belongs to the bus 1, device 4, and ls-usb -t. I have a bus 1, and here we have a human interface. We go to sys class USB, this is bus, sorry, bus USB devices. And what we have here is a directory for each USB device. The first number is the identification of the bus, and then we have a port structure in the tree. So in this example, I will check the port number. Oh, it's both human interface. But the device was 4. So this is the last one. So CD1. 3. Does it match? Yep, it matches. OK, so this is the device. Now I will go to the HCD directory, USB 1, echo 0, authorized default. Now I will disconnect my tablet and connect it once again. The USB device is connected, so ls USB. You see that the Dell is present. But now I will try to open terminal, and it is not working. If I will do ls USB -t, I see that there is no device 4, and there is no driver for that device. So now I may check if this is really a tablet or this is a pen drive, because I may do ls USB -v -d and check what I have really connected. I have connected a tablet, but it introduced as a keyboard, so probably I don't want to authorize this. But if I'm sure what I'm doing, I may go to its directory, echo 1, authorized, and now I will be able to open the terminal once again. So this is how the USB device authorization works. It gives the time to decide if it is really a device which I would like to use. So now the question, may I have my own USB device? May I take my tablet and introduce as I want? Well, yes, you can. Probably on a tablet, it's not very convenient to do this because you need some console access, and you have only a single port in your tablet. So I encourage you to use some developer board, like BeagleBone, Odroid, or even the chip. We need the implementation of the USB protocol. Linux kernel provides it, so let's reuse it. We need the implementation of some useful protocol. Like in this example, we had the human interface protocol, so let's go and use it. And we need some desired functionality provider. When we are using this HIT protocol, the functionality provider is a simple user space application which just sends the keystrokes through the device node. If we are setting, for example, the Ethernet connection over the USB, we simply may run any service which uses the network interface. So we can emulate this using our system infrastructure. A short introduction to the terminology. USB device consists of the software part, which is called the USB gadget, and the hardware part, which is called the USB device controller. UDC driver is, of course, a driver for this controller. And USB function is a driver which implements some useful protocol, for example, the HIT or the network. As device is a composed device, driver, USB gadget, is a glue layer which allows you to compose multiple functions into a single USB device. So how we can compose our device? Well, maybe first the big picture once again. We have our host, we have the bus, UDC driver, USB core functions, gadget driver. This gadget driver simply does nothing. It handles the generic requests based on the descriptors provided by the function and routes the suitable communication to the function drivers. And those function drivers provide something to the user space which can be used to provide the functionality. So you see that it is quite similar to the host-side implementation, as we also have here multiple drivers which provide something to user space that is usable to other applications. So what do you need in your kernel to use the features I'm talking about? Well, you go to kernel config and you go device drivers, USB support, USB gadget support, and you would like to choose probably USB functions configurable through config.fs. Then you have a set of functions which are available in current kernel. You choose which of them should be available on your board. What is really available? Well, we have the Ethernet emulation, serial, mass storage, so we can emulate a pen drive, human interface, video, audio, printer, phonet, and the development functions, loopback, and sourcing. So how to glue our functions into the USB device? First of all, we have to choose the identity for our device. This identity will be placed in the device descriptor. So we have the vendor ID, product ID, class information, and the strings. We need to decide what functions should be available to host when we connect this device. We need to decide how many configurations it will have, and decide which functions should be available in which configuration. How we can do this? First of all, we may use the bare kernel config.fs interface. Config.fs is a generic file system which allows you to create kernel objects and configure them. So we may use the file system operations. Here is the documentation to this interface, and set up our gadget. Well, yes, we can. But it's a little bit complicated and tedious to create the scripts which creates a directory here, creates it here, create the symbolic link from one place to another. So you need to know almost all about this interface, and it is not available in the this information about where to create, where I should not create, where I should do echo, where I should do symbolic link. It's not really easily available from the user space. That's why there is a helper library called libusbgx. So you may use this library and create a simple C program, which you will just run, and it will use this library to create your gadget for you. But it requires writing a C code. So if we can skip this step, let's do this. There is a tool called Gadget Tool. It allows you to create a simple script. You simply just call gt create gadget create g1 and all that kind of stuff. So you may use this to create a shell script, run the shell script, and everything should be set up. But it still requires writing a shell script. It still requires the knowledge about the order of the operations on the config.fs. So let's simplify this. Let's go to the declarative description of our gadget. This is what gadget schemes really are. It's a simple configuration files which allows you to declare, OK, I would like to get such device now. This file has a libconfig syntax. It's an example of the gadget scheme. It simply declares the attributes, so the general attributes of the USB device, the ID vendor, product, and the values from the device descriptor, strings, the language is the US English, functions. Here we have the one functions. It's Ethernet control modem, so we will be setting up the Ethernet over USB connection. We have one configuration, and this function should be available in this configuration. Those files are interpreted by libusbgx, so you don't have to use Gadget Tool. You may create your own application which uses this library and simply call the import function. But also can be used, GT can be used to load it. So let's try to compose this. To do this, I have an Odroid board. I don't know if you are guys familiar with it, but it's a simple development board with the USB device controller. So I will just, on the right side, I have a console, serial console to the Odroid. There is a file. It should be familiar to you. This is the same file as on the slides. So now I will just call gt load g1. It's the name of the gadget. File. OK. The device has been created. That might be not the device, the gadget has been created. Now, when I will connect my Odroid to the computer, Oh, probably I should change the authorized default. Okay. Now when I will connect this, we have the logs which says that the configuration chosen by the host is configuration number 1, LSUSB, and there should be our device. Yep, this is the one because it has the same vendor ID and product ID as I declared in the gadget scheme. And if config minus, shows us that we have one new interface. It's called USB 0 because we have connected a network card on the USB. So let's set it up. On the device side, we got the same. We also have the USB 0 interface. We also have to set it up. And now I should be able to ping or log in using SSH. Yep, you see the same prompt. So I have just logged in to my Odroid composite device, then use ifconfig to configure the interfaces on the both sides, and simply use the SSH or any other service to communicate with the device user space. So that's everything I got. I think we have some time for the questions. So if there are some, I will be happy to answer. Yep, maybe we'll try with the mic. Could you please pass the mic?
Hi there. I really enjoyed that. So when you did the sample right at the very end, what part of the JSON looking file said it was a network device?
Well, it was this part.
Yes.
It says that this function has the type ECM.
So ECM is some code meaning
ECM is some code, which means it's Ethernet control model. If we get back here, we have the family of Ethernet emulation functions, and ECM is one of them. So we may use any of those strings to create the ECM, the Ethernet over the USB function.
Right. So is that documented as part of the Linux USB gadget driver model, or
is that documented? Yes, there is a presentation, this one. And you may check those files. I think there should be some information in testing section,
right,
which function provides what to user space and how to use it.
I just wanted to find out, is that defined by you or USB-IF? It's defined by you, really.
Which one?
The ECM, so that string in there, the way you've written the GT script.
Okay. The ECM is the identification string, which you can get from the libusbgx sources. You can get this from the gadget tool. There is a command which allows you to show the identification string of the Ethernet functions. Or you may see the kernel sources. You go to drivers, USB, gadget, functions, and then you will get f, floor, something, files, and there will be a string which you have to use to create your function.
Okay, thanks.
No problem. Any other questions? Yep.
How would you normally trigger the gadget tool script? You know, a lot of times you're unplugging and plugging in devices. You know, you want to run that script, I'm guessing. Like, how does that get triggered?
Well, it depends if you'd like to trigger the script each time when you connect the device, all you'd like to trigger the script on the device startup. Because it is enough to trigger this once, until we reboot, everything will be working, even if you disconnect the cable and reconnect it. So there is no such problem. And if you like to use for example, execute different script each time when you disconnect and connect the device, you can use the xcon class and wait for the events from the xcon to execute the script. So any other questions? Yep. Does the block transfer involve DMA? Well, it depends on the implementation of the host and the device side, because I'm not sure which side of the communication you are asking. But usually, it's a USB device control role to decide whether it should use DMA or not. But usually, it does.
Can the device start the DMA, or does the host always hold the DMA? Is it always the DMA?
Whoa. If device starts the DMA, it starts the DMA on the device side. If host starts the DMA, it starts the DMA on the host side. There is no connection between those two.
So does that mean a rogue hardware device could instantiate a DMA to a invalid memory location?
Nope. Because if we are starting the DMA, if we are doing the bulk transfer, we are submitting something. So we have function creates a packet and pass this to the device controller, and this device controller starts the DMA. But this device controller starts the DMA on the Odroid, so on some device board, not on the host side. On the host side, we have a host controller which operates on USB request blocks, and it starts its own DMA, not the one on the device side or any other. So the controller on the host choose the address for the DMA, and controller on the device choose the address for the DMA, but that's different DMAs and different controllers.
Do you have any updates, or can you talk about?
Use the microphone.
The microphone, maybe.
Oh, sorry. Do you have any updates or status on 3.1 support in Linux?
Nope, I don't have any information about this.
Okay.
I know that recently there was some patches, but I'm not sure if they have been merged already. There was a question from behind, please.
Sort of on the same line as the previous gentleman. Are devices sort of memory mapped, or is data transfer happening through packets?
Well, device is not memory mapped. The transfer happens using the packets called on the host side it's the USB request block, and on the device side is the USB request. And usually the design is that you call the device controller, for example, or host controller, please allocate me a bunch of memory for the transfer. You place your data and schedule this to be sent by the controller. And the controller runs the DMA on that buffer or anything what it needs to do. And it is sent to the host, and host is receiving it to the bunch of his memory. But there is no direct memory mapping.
Cool, thanks.
Sure. Yep.
Are there front ends for the authorized stuff?
Yep, there are at least two of them. One of them is for sure on the GitHub. It's the USB guard project. It's the user interface for the authorized attribute. It simply does nothing more. There is a configuration file in which you need to write some rules, which device you would like to authorize and which one no. And I know that GNOME is doing something with this. I don't know where the repository is, but I have spoken with one of the people from GNOME, and their solution looks really good, I would say. They are even care if the desktop is locked or not when authorizing, so it should be nice. But I don't know when it will be ready or where the development is happening. Okay. Any other questions?
Is there any recent vulnerabilities in any of the device drivers that basically you can plug in a USB device and exploit that vulnerability to to gain access to the computer, like to write to memory or something like that?
Well, if there
Or
are
recently
some, they
known.
are being fixed continuously, so that's all I can say about this. Okay, any other questions? Because we're, yep, last one.
How is this going to help with a device that is plugged in?
Well, if the device is plugged during the boot, you have different options. If you said that each device during a boot should be not authorized, so you will use the kernel command line parameter, authorize default equal false, then it will simply start your desktop and you will have to authorize the default.
Usually you have a bunch of USB devices, having connected mouse, maybe, or a built-in camera.
Yeah, but this doesn't matter. If you use the command line parameter, it means that the value which I wrote to using sysfs will be by default set to false.
Yeah, so when I log in, I will have like a 10 or 15.
First of all, if there will be no static rules on the file system, you will be unable to log in because probably your keyboard will be not working. So you need some automatic daemon which will authorize the first keyboard, the first mouse, and then you will be able to log in and decide about the rest of the devices. The USB guard project works usually using the config files. So there is a set of rules in which you decide which device should be authorized and which one should be not.
And this is based on the assumption that the ports won't change, right?
Nope. There are different configuration options. You may use the ID vendor, ID product, the values from the descriptor, but you may also use the USB topology using the ports or the place in the USB hierarchy. Okay, so we are running out of time, so I have to make place for another speaker, but we may talk after the presentations. Thank you.